This is video 4 for the mechanical waves unit. Let's talk a little bit more about sound. Sound is a mechanical wave, so it needs a medium to travel through. This medium can be a gas, a liquid, or a solid. The medium itself has a lot of influence on the speed of the sound wave. So I have a couple tables here. This one's kind of important. So sound, when air is at 0 degrees Celsius, is 331 meters per second. When air is 20 degrees Celsius, it gets a little bit faster. So sound travels faster through warm air. Notice that through steel, it is 5,960 meters per second. That's very, very fast. One way you can kind of observe this, let's say you got your hand, or your ear, get your ear on a steel railroad tie, and 3 or 4 miles away, someone's tapping it with a small hammer. So in air, you would not be able to hear that sound. But through the steel, you'd be able to hear little tiny pings. And almost as quick, you'd hear it almost as soon as the person tapped it. It traveled very, very quickly. So let's say you need to calculate how fast, or get an idea for how fast the speed of sound is in air. This is a model you can use. So the speed of sound in air so 0.6 times T plus 331, where T is the temperature in degrees Celsius. So if I were to kind of construct a graph of T versus V, I would see that. Let's see something like that. So it gives us a way of calculating the speed of sound, and it's an approximation, but it's a pretty good approximation. Another property of sound, and really all waves, is something called diffraction. So this is the bending of waves around corners or passages. So if I have a flat wave going through an opening, it becomes circular. It kind of spreads. We also see this in flashlights. When you look at a flashlight or point a flashlight on a wall, the circle of light is much bigger than the opening of the flashlight. And we do have a way of calculating how much that spread is. So if I were to put some things down here, here's Y. It's dependent on the wavelength. It's dependent on the opening, and it's dependent on how far away your screen is. So this gives us a way of kind of calculating how much the wave would spread by. And again, take this with a grain of salt. It's a very big approximation. This is this can get very, very difficult math-wise. So we're not going to get too big into that. But I do want you to understand the property of diffraction and how waves spread when they go through an opening, or how they kind of bend around corners. Another proof of this, if you are standing behind a corner, you can hear someone talking without actually looking at them, because their sound waves are bending around that corner. Some more characteristics. We have its frequency. So, again, frequency is how many oscillations per second. And for sound waves, we can kind of break them up into 3 different frequency bands. From 0 to 20 hertz, we call this infrasonic. You probably cannot hear waves in the infrasonic range. The average human can hear sounds from 20 hertz to 20,000 hertz. So we call this audible. A good test of this, the old cathode ray televisions, the great big boxy televisions. As a kid, when you're watching, you probably heard this annoying little high-pitched whine. And if you asked your parent about it, they probably didn't know what you're talking about. That's because that pitch is right at around 20,000 hertz. And when you're a young kid, your ears are very good, you can hear those high frequencies. As you get older, your audible range begins to shrink. You can't hear 20,000 hertz. You can't hear 20 hertz. So your entire range begins to shrink. 20,000 hertz on up, this is what we call ultrasonic. Bats and dolphins tend to use some sound waves in this frequency. So there's a lot of sound waves that we cannot hear. But there's a lot that we can hear. So, even though we can't hear infrasonic and ultrasonic, we still call them sound waves. They are still a disturbance in a medium. When the medium and temperature of the medium are consistent, all three types will travel at the same speed. So animals that use echolocation will typically use ultrasonic. We also use ultrasonic waves for ultrasounds, to look at fetuses inside of pregnant mothers. The way that animals use echolocation, they send out ultrasonic waves. Those waves bounce off of something and then return to the animal. And the reason why they use ultrasonic is because infrasonic and audible, the wavelength is too long and diffraction happens, and the wavelength bends around that object and doesn't get fully reflected. So the animal wouldn't, it'd be like the animal seeing something fuzzy if they try to use audible waves. So you have to use very, very small frequency, very high frequency, very small wavelength waves. And next we have frequency versus pitch. I kind of alluded to this earlier. Pitch is the perceived highness or lowness of a sound. Frequency is the scientific measurement of it. Another important topic is loud. How loud is a sound? How do we measure loud? Well, in physics, instead of saying something is loud, we say it's intense. So we're looking at the intensity. This is generally related to the amplitude. So sound intensity is the rate at which energy flows through some unit of area that's perpendicular to the direction of the sound wave motion. So this will obey an inverse square law. So as you get farther away, notice that you're covering more and more surface area. So if you are like 1 meter away, we can measure how intense. If you're 2 meters away, well, now that area is 4 times larger. So the sound would be 1/4 its original loudness. If I'm 3 meters away, well, now I've got 9 units of area to cover, and the sound is only 1/9 as loud. So we have an inverse square law, just like with gravity and electric forces. Now for intensity, we have a couple thresholds. First off is the threshold of hearing, and this is the quietest sound that you can hear. So this is 1.0 times 10 to the negative 12th watts per square meter. So intensity, again, it's kind of based off of power. Power's energy conversion, and square meter. So we get square meter. That's where we get our inverse square law. Now we have the threshold of pain. This is a sound that if you heard this sound, you would be in physical pain. So it's pretty simple. It's just 1 watt per square meter. So just as frequency determines pitch, intensity determines loudness, but volume is not directly proportional to intensity. So a sound that's twice as intense is not perceived as being twice as loud. The sensation of loudness is approximately logarithmic in the human ear. It's not perfectly logarithmic, but it's approximately logarithmic. And also, you probably have never seen this unit for volume before, watts per square meter. And also, it's a very, very tiny. I mean, if we keep everything between those two thresholds of hearing and pain, we're talking about 10 to the negative 7th, 10 to the negative 11th, 10 to the it would be very inconvenient. So we normally don't use watts per square meter to measure how loud something is. And you probably have heard this before. We use decibels to measure how loud something is. So what exactly is the decibel then? So it's one way of measuring intensity. And it does this by relating the intensity of a sound to the intensity at the threshold of hearing. So, the way we calculate this, the volume, measured in decibels, is equal to the number 10 times log of the intensity of that sound divided by the threshold of hearing's intensity. So if I were to plug in the threshold of pain, 1, and plug that in there, we would calculate that the volume in decibels for the threshold of pain is right around 120 decibels. Now, a difference in 10 decibels means that the sound is approximately twice as loud. So the volume doubles each time the decibel level increases by 10. Sounds at the threshold of pain, which is about 120 decibels, are about 4,996 times louder than sounds at the threshold of hearing. So this is a quick little graph or thing here. So if I put in the threshold of hearing up here, so if I had 1 times 10 to the negative 12th divided by 1 times 10 to the negative 12th, that equals 1. Well, log of 1 equals 0. So the threshold of hearing has a decibel level of 0. A loud car horn is around 90 decibels. And notice up here 125 is about a threshold of, about the intensity of threshold of pain. So we have some different things here. If you are, I think it's 80 decibels or louder, if you're exposed to that for a long period of time, it can cause damage. So a lot of times if you work in a factory, they'll make you wear ear protection. Now the loudest that any sound can be is 190 decibels. That's it. And that's because sound is a compression wave. And at this volume, the air molecules stack together and the compression wave can't move. So remember, for compression waves, the thickness of the compression is their amplitude. Well, at 190 decibel levels, the amplitude gets so big that the sound wave physically cannot move. So it's at 190 decibels. That's the loudest that a sound can physically be. Okay, so the last topic I want to talk about is forced vibrations and resonance. And I've got some demonstrations I'll show you in class to give you a feel for this. So a forced vibration occurs when energy from one oscillating system is transferred to another, usually through sound. Sympathetic vibrations occur when energy from a vibrating system is transferred through the air, causing another system to vibrate at the same frequency. So an example here, if you have two tuning forks that are the same frequency. So here's one tuning fork, and it's I don't know, 400 hertz, and it's vibrating. If I bring in another tuning fork that is also a 400 hertz tuning fork, the energy, or these vibrations, will travel through the air molecules will hammer into that one, and then pretty soon this one will start to vibrate as well. So that would be sympathetic vibration. The only way for this to work is if they both have the same frequency. So if I brought in a 500 hertz tuning fork, the 400 hertz tuning fork would not be able to get the 500 one to start vibrating. Both of them have to have the same frequency. A forced vibration is, if you were to take a tuning fork and set it on like a box, if this one's vibrating, eventually it's going to force the box to vibrate at the same frequency as well. Guitars and pianos do this. A string is very quiet, but if we attach the spring to a larger box, it gets the larger box vibrating, and then that sound can become louder because a bigger thing is vibrating. So that's forced and sympathetic vibrations. A natural frequency. This is a frequency an object will naturally vibrate at. A lot of things have a natural frequency. Glasses, bridges, road signs, tuning forks. The natural frequency of a 400 hertz tuning fork is 400 hertz. Some objects have many different natural frequencies, like a guitar. It has a lot of different natural frequencies, which is why it can vibrate with many different strings. So that brings us to resonance. This is a condition that exists when the frequency of a force applied to a system matches the natural frequency of that object. So a good example is when someone runs their finger around the rim of a wine glass, causing a sound. Now, when an object resonates, it is vibrating at its natural frequency. And if it continues to receive energy, the amplitude will increase, and it may cause the object to explode. So this would be that classic example of the opera singer busting a wine glass with his or her voice. They're matching the natural frequency of the wine glass. Once they've matched it, they then continue to pump energy into it, getting the thing to vibrate more and more wildly until the atomic bonds in the glass can no longer contain it, and then it explodes. So I'll try to show you guys some cool YouTube videos of that happening, because it is kind of fun to watch. All right, that's going to conclude our unit on mechanical waves.